in this animation here, you can see that the landmass of the Earth here is tiled in small tiles, and you can see the amount of satellites of this constellation which they are using, in this case the global star one, denoted by color. And let's look actually how they technically pulled this off. But a side note here, none of this information is available publicly or confirmed. This is basically what I found out by reading FCC filings and some hacker forums. So take it with a grain of salt, but I'm quite confident that this is not too far off. So how it works is they designed a custom waveform, both on the smartphone and the gateway. And they are, in a case of an emergency, you can send a message via the L-band, that's 1.6 gigahertz, and you transmit that message to a satellite, and the only thing the satellite does is just relay that message, the waveform, without any changes except frequency conversion to the gateway. And then the gateway is connected to some kind of emergency center, and they can respond also in the other direction, so it's a kind of full duplex system. And on downlink towards the phone, they're using S-band, which is 2.4 gigahertz. And I believe they're using a custom chip for the upload, but I'm not sure about that. And it's quite interesting to look at this waveform and its properties. So from FCC filings, I think it's 200 kilohertz bandwidth and quite low power, and using LTE-like uplink format. And that might be interesting when we look in a second around standard-based non-terrestrial network communication. Well, there are other proprietary mobile satellite solutions. One solution was proposed by Snapdragon, by Qualcomm. Their service was called Snapdragon Satellite. However, that is now cancelled, and it's quite interesting because Qualcomm makes those modems, those high performance 5G modems, which are also used in the Apple iPhone. And somehow Apple won this race against Qualcomm, even though the Qualcomm's technology with the Snapdragon satellite is in the iPhone already, but still they cancelled it. Another thing which is quite popular is the Garmin InReach service. They use the Iridium satellite constellation network to also relay emergency messages. And there are also different approaches. For example, Skylo uses wants to use a different constellation of medium Earth orbit satellites. And there's even another different thing from the Chinese, and they want to use their GPS satellites for relaying the emergency messages, so the Beidou system. Well, this was proprietary. Now let's look at standard-based solutions. So there are basically two main players here at the moment who announced publicly that they're using standard-based non-terrestrial networks. And one is Starlink. They are using LTE on their new direct-to-cell satellites. It's not clear whether the modem is actually on ground or on the satellite. And there's a different one, AST Space Mobile, and they have a different approach. They are building satellites with extremely huge aperture antennas. To basically, the idea is to optimize the link budget and get the biggest gain to maximize the data rates for the end user, because we'll see in a second that the data rates at the moment are not too high. Okay, now let's look at actually non-terrestrial networks in the standard. So when have they been integrated in the standard? If we look at the evolution of the standard from 1G to 5G, we can see that the technology rapidly evolved and lots of changes in the waveform happened from GSM, GPRS, Edge, and so on. The metrics in terms of data rate, downlink, uplink, latency, and also the physical signal changed quite a lot until this point in 5G with the release 17, where they officially introduced non-terrestrial networks to the standard. So that was release 17, that was closed roughly 1.5 years, nearly 2 years ago. And now it's really a firm part of the standard. So it's not a vision anymore, but it's already included in the standard and it's being optimized and updated for further releases. And now phrase NTN quite a lot, but what are its actually use cases? And there are quite a lot. So you have basically 3 categories: urban area, rural area, and remote area. And There are multiple use cases in each area. For example, if we start in the urban area, we have the IoT use case. We have the availability to do a network backhaul, for example, where you use 5G not with a smartphone itself, but just as a backhaul via satellite, a standardized backhaul, so that you don't have to use a proprietary solution. You can use connected cars. For example, in Germany, we have a project going on at the moment with automated driving, where we want to make sure that cars which are sequential on the street have connectivity between them. And there is quite a consensus in Germany that, for example, if you do this on the Autobahn, it's not possible to have this stable connection because there are so many gaps in the network, so in the terrestrial network on the Autobahn. So NTN is the only solution to provide a stable connectivity here. But there are also other use cases like rural area, where you just want to provide internet to regions where there is probably no near terrestrial base station. And there are even more use cases like maritime, where you provide internet to ships, planes, and so on. Okay, now let's look actually at the hard truth regarding performance goals, what they envision to achieve with NTN. There are essentially two important lines here, or rows here in this table. There's the pedestrian and the vehicular connectivity line. So if we look at the first row, pedestrian, downlink and uplink, 1 megabit down, 100 kilobits up, it's not so much, right? But we have to say that this works, or is envisioned to work, with an unmodified smartphone. So that means handheld and no specific antenna. And the reason for this we'll see in a second is the link budget, which is really quite small. It's different for vehicular connectivity because the key here is that you have a very small aperture terminal antenna and don't rely on those negative gain antennas in your phone. And this way you can have a much stronger link budget, and it's at the moment envisioned to have 50 megabits down and 25 megabits up, which is actually not bad, I would say. So how do we get those numbers? Of course, the answer is link budget. And I've calculated here the link budget for two cases, LEO and GEO, so low Earth orbit and geostationary Earth orbit constellations for both downlink and uplink for the handheld category. And we can see, for example, for the LEO case in the S-band, the signal to noise or the carrier to noise ratio is just 6.6 dB. And given a bandwidth under ideal conditions, we can calculate the maximum theoretical data rate according to the channel limit, which is around 22 megabits per second. Well, this number is quite significantly higher than the 1 megabit per second above, but one has to say this is just an ideal assumption with full resource utilization dedicated for this one device, no interference, no frequency use, and so on, in an ideal channel. For uplink, the link budget is even worse. If we look at LEO, we get around 2 dB SNR, which results in only around 160 kilobits per second. And if we actually look at the geostationary case, where the distances are much, much wider, we get a horrible link budget of roughly minus 11 dB, which is 1 part signal, 10 parts noise. And with this, the theoretical limit is just in the amounts of a few kilobits. But anyway, so I would say it's better than nothing, and this works really for a handheld device. Okay, now we got some context regarding 5G and what they envision regarding performance, and now we can look about how the satellite architectures of the network look like. If you ever looked into 5G and documentation and books, you will find out quickly that there are so many abbreviations that you basically can't understand nothing. So here, instead of going through this, I want to give you a really short primer, try to explain it very simply from the base station perspective. So we have essentially 4 main components in the 5G system. We have the smartphones, also the user equipment. We have the base station. They communicate over a defined standardized interface. We have the 5G core network, where the goal or the sense is that you can connect multiple base stations to one core network, and each carrier owns its own core network. And this way you can distribute multiple base stations over the country and connect them. And we have the data network, which is connected to the core network. So internet is served via the core network to the base station, to the phone. Well, now what's inside the base station? Of course, there are the 5G layers, and they are the same in the downlink and uplink direction, roughly. There are multiple levels of abstraction. It's similar like the ISO-OSI model. We have some higher layers that do administrative stuff, for example, charging of the customer. And we have lower level layers that go more to the radio side, for example, starting with the MAC layer, PHY, and then the RF side. From that perspective, it's pretty simple. Every block does its job. And one thing which we can do now is we can make a split, and we can divide the base station into two parts and have a central unit and a distributed unit. And you might ask yourself now, why would we want to do this? It's already complicated enough. Why do we have to split the base station up in two parts now? And the basic idea here is that, for example, if you look at the satellite architecture, if you want to deploy this base station really in space on a satellite, you can imagine if you put the full base station on the satellite, you have to have extreme capabilities in terms of processing. And any chance to reduce that processing burden, and this idea here is to outsource some processing layers, in this case the higher layers, and get them off the satellite to the ground. You can save, or you can make your satellite architecture weaker in terms of processing power. You don't have to have such high requirements, and the system gets simpler. One note here: this boundary is not. There are multiple options where you can place this boundary, and there are advantages and disadvantages. For example, if you place this boundary very much to the left, the distributed unit has lots of capability. And one use case is, for example, if you have two devices connected to the same satellite and they want to communicate with one another, if the satellite has lots of base station capability, it can just reroute the signal without going to the core network on the ground, just reroute it from one phone to another. And that saves lots of propagation time. However, if you, for example, make the distributed unit only owning the RF component, then of course the whole IQ stream has to go to the central unit, and there's less capability in the satellite. So now, what are the split options? Just to give you an idea, I just said it, there are multiple options. You can make a split quite high between the administrative layers. For example, there's one thing called F1 interface, where the bandwidth of the split is 4 gigabits per second, and you can do exactly the opposite. You can make a split really low between the PHY and the RF layer, where you obviously the interface is now the raw IQ samples, and you can imagine the data rate explodes, and the number here is 160 gigabits per second. I think that was for the first release of 5G. It's now probably much, much higher. And you can do something in between. Here we have the PHY layer detailed with its processing components, coding, rate matching, scrambling, modulation, and so on. There are a lot of different physical layer blocks, and you can make the split even in between here. There are multiple options, and the split has also another advantage. For example, if you look at how you deploy the space station on a hardware, it's not like you're just going to put this program on a CPU and run it. This is not going to work. You have to distribute the base station processing on a heterogeneous system to exploit hardware acceleration for physical layer signal processing, or the generic properties of CPUs for non-parallelizable administrative layers. And you could imagine the benefit is when you have a defined split in the standard, then it's not going to be a proprietary solution where you take your split when you deploy your architecture. Okay, now, interesting two categories, 5G NTN architecture. There are basically two ways how you can design your system. One thing is using a transparent architecture, similar thing as Apple does. The satellite basically acts as a relay. There's no significant processing power on the satellite except mixing frequencies and up-converting a signal up and down, but nothing else. And in this case, the base station, it's called gNodeB, is on ground next to the big gateway antenna. And in this case, the 5G waveform, the 5G new radio waveform, which is between the smartphone and normally the base station, is used both in the uplink to the satellite and in the downlink to the gateway. That's the simpler architecture option. The more complicated architecture option is using the regenerative satellite. Regenerative means the satellite has processing capabilities to really decode and demodulate the waveform and generate a new waveform. And in this case, you have the 5G new radio waveform between the phone and the satellite, and you have a different specialized waveform just for the backhaul to the gateway. Well, you might ask yourself now, which one is better? Which one should we choose? One is obviously much more complicated. Are there any benefits? And to answer this question, I developed a case study for this presentation about vehicle-to-vehicle communication. And the reason is vehicle-to-vehicle is because in Germany, everything is about cars, and we have this project going on, so that's a good way to get funding for research also to apply to 5G non-terrestrial network. And now if we look at the round-trip time of this vehicle-to-vehicle communication for the regenerative and transparent architecture, I said it before, for the regenerative, I brought this example that you can just go up to the satellite and down to the car. You don't have to go back to the gateway on ground and save essentially half of the propagation time, which is really useful. So in LEO you get around 61 milliseconds, and note this is really the round trip time. So this is from one car to the other and back. And for GEO you get a second, which is really quite high, right? Okay, so here for this scenario the winner is clearly regenerative. Now it gets more difficult. What if we have an inter-gNodeB handover situation, meaning the car leaves the zone of one satellite and enters the covered footprint or zone of another satellite? In this case, you have to follow the 5G handover procedure. And for illustration purposes, I analyzed the 5G handover protocol and the time it takes to basically perform this protocol. And you might see in this image there are lots of messages sent between all those components. So between the car and the old gNodeB, between the car and the new gNodeB, between those two gNodeBs on the satellites and the core network, and between those gNodeBs themselves. And if you just count the timing of those messages, you will see that the transparent architecture actually is faster here by around 50% than the regenerative architecture. And the reason why this is because there is lots of connectivity between the gNodeB and the core network defined in this handover protocol, which means in any case from the satellite you have to send a message to the core network, so you have to go back anyway. And you don't really have a benefit here of the regenerative system. However, there is an update in the standard where they define inter-satellite links between two satellites now. It's via the XN interface. And this allows two gNodeBs to directly communicate with one another without going back to the core network. And using this feature and the new handover protocol, we can actually see that we can get rid of this problem, and now both transparent and regenerative are roughly the same again in performance. It's actually a little bit faster for the regenerative case thanks to this inter-satellite link. So last thing is intra-gNodeB handover, which is actually also really interesting. As you might know, with terrestrial systems, terrestrial base stations divide their environment with sectorizing antennas to reuse the spectrum multiple times. One common angle was 120 degree. I believe it's already 60 degree nowadays. And the same thing happens for satellites. They don't use like those triangular regions, but they use spot beams for that. So if you imagine on the right image, you can see multiple satellites, 7 satellites here. And each satellite has its own small sectors which it covers and where it reuses its full spectrum in. And if we look at the radius of those sectors, this is roughly 20 kilometers, and this is based on the technology which new satellites like Starlink use. They have a spot beam radius, of 20 kilometers. If we compare it with the satellite ground speed of roughly 7 kilometers per second, we see that the sector changes for stationary objects all 2.7 seconds. Now, if we think back of those propagation times, which you saw on the slide before with the handovers, and we know that this was hundreds of milliseconds in some configurations, this can be quite horrible if all the logic that organizes this handovers is on the ground and not on the satellite. So there could be lots of outage times introduced if the satellite is not able to dynamically handle this in orbit directly. So that's another benefit of regenerative systems. Okay, last case, what's the round trip time if two cars are in different satellites? It's pretty simple. There's a factor of 40% increase for the regenerative case because they can use the ISL link and don't have to go back to the core network 2 times to transmit the message. So I think you notice that I'm quite a fan of the regenerative architecture, and that's why I want to go now, provide lots of context now into how we can actually realize this base station on the satellite hardware. And of course, in space, all the hardware has to be space grade. So we are building this gNodeB on Airbus' new satellite telecommunication processor, which is based on AMD Xilinx Versal platform. And the Versal is an adaptive system on chip, which has a CPU, an FPGA, and also lots of small vector processors. And for the 5G base station, we use the Open Air interface, which is an open source 5G framework. It has also a virtual user equipment and the core network. But for this, we only need the base station actually on the satellite. And yeah, that's basically the architecture. And a trivial approach would be now to just put the Open Air interface on the Versal, only on the CPU, and see how it goes. Well, we did this at the start, and if we look now at this diagram here, we did a profiling of the software on the CPU. We can find that lots of CPU resources are used up by physical layer signal processing. In this case, roughly 20% is used by 25% is used by DFTs, and IDFTs, so Fourier transform. Others is used by LDPC and math, and only a few is used for the higher layer processing. And the first improvement, one would say, is get rid of this physical layer signal processing on the CPU, because obviously it saturates the CPU far too quickly to achieve any meaningful capacity. So this is what we did. We outsourced for the start the FFT and the IFFT from the CPU to the FPGA using IPs from Xilinx and analog devices. And we saw directly a reduction of around 20% in the CPU resource utilization, which is really great because this tells us that this approach is working. We tried this out for 3 different waveforms. For the smallest waveform available in the standard, that's 5 megahertz bandwidth, and for one of the bigger ones, 40 megahertz bandwidth, around 60 megasamples per second. And we saw for the small and the medium waveform, we actually achieved a CPU reduction of 20%. But for the fast one, we see there's basically no CPU reduction achieved, 93% to 91%. And you might ask yourself why. Well, the reason is the CPU is still saturated even after we get rid of those FFTs, because it's still not real time and still tries to keep up as fast as possible. All right, so now that I've shown you the approach, let's look at the big picture. So how would a gNodeB, an optimized gNodeB on a next generation telecom satellite processor look like? Well, the processor has a few components, has a control unit, an RF front end, a regenerative module for some specific waveforms that doesn't matter for this year. It has a multi-core CPU. I'll get to that in a second, why we have that now. And it has obviously the Versal. So, and they are all interconnected via fiber and space wire, and this system is called the THEA processor. It's designed by Airbus Defense and Space in the department where I'm currently located. And for the gNodeB, we need those 3 components. We need the Versal, we need the multi-core CPU, and we need the RF front end. Well, now the question is why is this multi-core CPU now coming in? As we've seen before, the Versal CPU is quite easily saturated with tasks, and we did some analysis and found out that even if we only use the higher layers on the Versal, that we can't achieve meaningful capacity because the Versal only has a dual-core ARM processor, A72, which is not fairly strong. So the idea is now to outsource the higher level 5G processing to a real multi-core processor and use the Versal's FPGA and maybe even the accelerator, the ASIC accelerator for the physical layer. So how does it look like? Let's build this picture up. So the gNodeB is now obviously distributed with a design partitioning on the Versal and the multi-core CPU. And one note is that we actually use the distributed unit and the central unit for our gNodeB. So we have the full capability on board the satellite. It's not that we only use the distributed unit, as I said before. That's an option. And with this split, this would be then the interface on the backhaul. However, we do the full distributed and central unit to have full capability here. Okay, what do? The lower 5G stack, we have the physical layer, we put that on the FPGA of the Versal. That's quite obvious. At the moment, on this slide before, there was only the FFT on the FPGA, but we can do the full physical layer in an accelerated fashion. On the CPU, there is only data orchestration and management of the FPGA, so the CPU of the Versal is essentially free now, which is good because it's not strong enough to handle any significant processing. On the other side, now on the multi-core CPU, we deploy those upper layers of the 5G stack, so everything starting from the Mac, RLC, and so on, everything above. And we realized here a phi-mac split. So when we go back to this splits which I introduced earlier, we can see now on the Versal we have the physical layer, and on the multi-core CPU we have the Mac layer. And this is called a phi-mac split with a defined in the standard with a defined interface. So everything here is standardized and there's no proprietary component in this architecture, which is quite good. So the last, and they communicate via PCIe, so they have a strong bandwidth interface here. The last thing we need is the RF front end, and for that we're using the Analog Devices 9082 chip, which is quite a strong RF front end with 12 gigasamples DAC and 6 gigasamples ADC, and this is sufficient to handle a full gNodeB from the RF capabilities. And they communicate via JESD protocol, which is also implemented on the FPGA of the Versal, which just makes sense because the data comes from the physical layer, right? So the data is located on the Versal already. So moving the data again in the system does not make sense. So with this solution, we have the opportunity to realize the communication protocol IP directly on the Versal, on the FPGA itself, so we reduce any communication. And in the keynote yesterday, we heard communication is the main bottleneck for high power computational systems. Another thing to note is that the Versal is actually optimized for AI processing. So this is just a side note. But if we want to, we could deploy neural networks directly on the chip itself and could perform neural network inference in space. And there is already work in the standard going on of how machine learning might be integrated in the base station side to, for example, do some augmented processing of some metadata or some resource orchestration or stuff like that. And our architecture basically would enable this inherently. Well, last note to the RF front end. The protocol is the JESD 204C protocol, and as I said before, it has 4 digital to analog converters and 2 ADCs. And it's even possible, the interesting thing here is even possible to stack those things up because it's possible to connect them with the same clock source. So this way you could even deploy multiple of those chips on the satellite itself and use that for beamforming, which is a strong feature that came with 5G. Okay, lastly, I want to invite you to check out our 5G NTN demo in the exhibition. So I actually brought the lab equipment with me for the conference, and I can show you and tell you a little bit more about the hardware platform and show you a link between the base station and the virtual user equipment. All right, last concluding words. I think the future of space communication is going to be really bright because NTN is definitely going to come and it's going to revolutionize satellite access, because everyone will now have the possibility to talk with satellites with a standard $200 smartphone that supports 5G. And this is really something which has not been there before. And lastly, it will be for the better of anyone. So I hope I got you excited, and I really am. And if you have any questions, feel free to shoot them at me. Thank you very much.
Do you envision making use of GPUs at all in this architecture for accelerating some things? Because I noticed in the high-speed one, you were still, hitting your performance limit, and I was just curious to
So-
know if GPUs.
Yes, that's a very interesting approach because obviously there are also embedded GPUs developed by NVIDIA like the Orin series. The one main factor which is why Airbus is holding back on those GPUs at the moment is that they are not inherently compliant for space radiation. That's the main point. However, there are third-party studies, for example, at the University of Barcelona, and they are currently testing the radiation resistance of the board, and it actually looks promising. So I'm trying to push this a little bit, but you know the space sector is really dominated by FPGAs, and another solution would actually to use a soft GPU implementation on an FPGA. There are also specifically in the space sector implementations for that. So we'll see how it goes. At the moment we stick to FPGAs, but I agree GPUs would be interesting.
Yeah, thank you. So I've got two questions. So the first one is, how did you have to modify open air interface to get it running on the dual core A72 compared to the main branch?
Yeah, very good question. It actually doesn't work to just use the software from the internet because it's made for the x86 architecture. So we had to modify, the open air interface uses some assembly instructions to vectorize some processing. So we obviously had to port those manually to ARM instruction set, the ARM v7 instruction set. And another thing is to outsource this physical layer signal processing components. We had to directly go into the C++ code base and throw out in our case, the FFT implementation and call our FFT IP cores. And that's basically manual work in that sense.
How are you realizing the feeder link, SRI, on the presented platform?
Yeah. So the feeder link is still actually in question. We have not thought too much about the feeder link because there's also some development in the standard going on of what protocol the feeder link might use. So there's obviously one option is to use some standard-based protocol like DVB-S2, or to use another one is to use a proprietary feeder link. But at the moment, we're waiting a little bit of how the standard evolves because obviously a feeder link is an integral part of the system, and ideally we would want to use that.
I do have one myself. So Airbus is a large defense corporation mostly. How does working with open air interface and working in the open actually work? Are you able to feedback, for example, your modifications on open air interface that were necessary? Is there some process that you need to kick off, or how does that work?
Yes, the open air interface is heavily maintained by Fraunhofer, and they are quite near to us, 1 hour by car. And we have multiple projects going on with them. One is this, it's called 5G AutoSAT. This is this vehicle-to-vehicle communication. And for example, when we integrated the RF front end, this was not given from the open air interface. There were a few SDRs supported. There was, for example, the Etus SDR supported, Blade RF, and so on. And what we did, for example, we integrated the libIO library of analog devices. And this is something we're going to feed back to the open source GitHub community so that hopefully everyone could profit from that.